Hi all, today we discuss 6.20. This is a theorem. This is a connection between integration and differentiation. A famous theorem connecting this integration and differentiation is fundamental theorem of calculus. So that is connected with this Riemann integrability. So we proved this theorem after this theorem 6.20. In theorem 6.20 there is a function f belongs to R on AB. It's a Riemann integrable function. For a less than or equal to x less than or equal to b, we put f of x, or we define a function f of x that is integrate to x f of t dt or f of u du. Then this f is, capital F is continuous on AB. Okay, if this small f is integrable on R, then capital F is continuous on AB. Okay, moreover, small f is continuous at x naught, then this capital F is differentiable at x naught. In fact, that derivative is capital F dash x naught is small f of x naught. Okay, this is the theorem. So we start with f belongs to R. This is a Riemann. This is the proof. This is a Riemann integrability. We have to prove that this capital F is continuous on AB. If capital F is continuous on AB, then that continuity is uniform continuity. So in fact, we will prove the uniform continuity of this capital F. Okay, so in order to prove the uniform continuity, we start with this f of f belongs to R. Then we know that this f is bounded. F mod f of x is less than or equal to some m. So this is f is bounded. Otherwise this will not be Riemann integrable. Then boundedness is a necessary condition for Riemann integrability that we have. You might have seen this in your 6th semester classes. So using this fact, we can get a constant that is m. So this capital F of x is less than or equal to the small f of x is modulus of small f of x is less than or equal to m for all x satisfying this condition, a less than or equal to x less than or equal to b. Okay, now if we choose some x and y, x is less than y less than or equal to b, so we choose x and y from this interval AB, then what is this capital F of y minus capital F of x? What is the modulus of this? So by definition, this capital F of y is integral a to y small f of t dt, minus this is integral a to x f of t dt again. Okay, so this is the difference. Now using the additive property of this integral, we can consider this is our AB, and we have x here and this is y. Then integral a to y minus integral a to x, that will be integral x to y f of t dt. So in fact this is integral x to y, this is our integral x to y f of t dt, but we know that this is always less than or equal to this capital M times y minus x. This is y minus x, and this m is capital, or you can write it as m times mod y minus x or mod x minus y, both are the same. Now this proves the continuity of this capital F, because if we have any epsilon greater than 0, for epsilon greater than 0, choose delta as epsilon by m. Okay, now we have mod f of y minus f of x equal to m times mod y minus x is less than this m times epsilon by m, which is equal to epsilon whenever this mod x minus y is less than delta. Okay, delta is chosen as epsilon by m. So whenever this quantity is less than epsilon by m, so this quantity will be less than epsilon. So this proves the continuity of f on the interval AB. Okay, now our next assumption is f is continuous. The small f is continuous at x naught. At that point we'll prove the differentiability of this capital F. Okay, so next assume that f is continuous at x equal to x naught. This x naught is a point inside that closed interval AB, so we assume the continuity of that small f at that point. So by the definition of this continuity, for epsilon greater than 0, there exists a delta greater than 0 such that modulus f of t minus f of this x naught is less than epsilon whenever mod t minus x naught. Okay, so mod t minus x naught less than delta. So this is the continuity of this f, the small f. So this is true for any a satisfying this. So any t satisfying this, a less than or equal to t less than or equal to b satisfying this condition, we can get this quantity is less than a pre-assigned quantity epsilon. Okay, so using this fact we will prove the differentiability of this capital F. Okay, to prove the differentiability of this capital F, we choose this is a less than or equal to this. We write it as we chose points from x naught minus delta less than s, less than or equal to x naught, less than or equal to t, less than x naught plus delta. We have chosen s and t in such a way that this inequality. So using this s and t, in fact this s and t are from this interval AB. Okay, we have chosen such s and t, and now we prove this capital F of s minus capital F of t minus s minus t. This is the divide difference formula. So we write it as t minus s because this t is greater than this s, so both will work anyway. So this is t s t minus s here minus this f of small f of x naught. Okay, and we will prove that as t tends to this x naught or s tends to x naught in both case, or s and t tend to each other, we will prove that this quantity tends to this f of x naught. So this quantity, this divide difference tends to f dash of x naught. Okay, so we can prove that capital F dash of x naught will be small f of x naught. So our intention is to prove the limit as t and s close to each other. Okay, now we evaluate this. By definition, this is what is f of t. We write this 1 by t minus s times this f of t minus capital F of t minus capital F of s. Then capital F of t will be integral a to t f of t dt minus integral a to s f of t dt again. This is the definition of capital F. Now we write this f of x naught. F of x naught is a constant, so we can write f of x naught into 1. Okay, and that 1 can be written as integral s to t 1 dt. Okay, so this is the modulus right now. We know that this this quantity is 1. When you integrate this, that will be t. Then from t s to t we can get that is t minus s. We write it as this divided by t minus s. Okay, or you can put it as u as the variable of integration, or this makes sense anyway. Integral of 1 is t, then substitute for the t as t, then minus s, so that will cancel each other because they are not equal, because this is a relation between s and t. So this will this f of x naught can be taken inside this integral because that is a constant value. So we can simplify this modulus as modulus of 1 by t minus s, and this integral is changed to, this is a and this is s, this is t and this is b. So the first integral is from a to t and the second is from a to s. Then the difference between these two integrals will be integral s to t. So we write it as a single integral s to t f of t dt, and we change this integral as this is 1 by t minus s. We will take this f of x naught inside this integral, so that will be integral s to t f of x naught dt. Okay, so this will be the modulus. Now we combine these two integrals, then that becomes integral t minus s, integral s to t f of t minus f of x naught, this is f of x naught dt. Okay, now we know that the modulus of the integral is less than or equal to integral of the modulus, so that will become less than or equal to 1 by t minus s integral s to t. Since this t minus s is positive, so you need not write the modulus here. So modulus of f of t, this is the integral of the modulus, f of x naught dt. Okay, but we know that this quantity is less than epsilon. Okay, we have chosen s and t in such a way that that 2 points lie inside this delta interval, so that x naught minus s and x naught minus t can be made less than delta by 2 or delta. So we will write it as or we can prove, we can write this t as u because there will be a slight confusion. There is already t is in the limit of the integral, so we write it as u. So we write this is u and this is also u. So f of u minus x naught, f of u minus f of x naught is less than epsilon. If we take u from this variable of integration is from this interval, so that is always less than delta. So we write this as 1 by t minus s integral s to t. This is less than epsilon, so epsilon t, that is equal to this epsilon can be taken out, then that will be integral, and you also replace this t by u here. The variable of integration is also u, so we write this is u. Here we have u. Here also we will use u here. Okay, instead of writing t, we write this u. Okay, so this is u, this is u, and here we have u, f of u du, this is u du du. Okay, so this will be epsilon. Now this can be made less than epsilon. So as t tends to s, or if we chose t minus t and s are very close to this x naught, so this will be very close to small f of x naught. So this shows that capital F dash of x naught will be same as f of x naught. Okay, so this proves the theorem 6.20. In the next class we will discuss fundamental theorem of calculus, so that will give the connection between integral and differentiation. So this is also this can be considered as a lemma for the theorem, because this is mere connection between integral and derivative, because the theorem shows that this shows that d by dx of dx at x equal to x naught, this capital F of x naught, that is equal to small f of x naught. So this is in fact d by dx at x equal to x naught, capital F of x. So this is capital F of x. This capital F of x can be replaced by integral a to x f of t dt. Okay, so this is f of x naught. So in this way you can consider this as a relation between the integral and the differentiation. So in the next theorem we will prove the fundamental theorem of calculus, in which we can see the way in a method to evaluate the integral. Okay, so that is integral a to b f of t dt can be written as f of b minus f of a using this function capital F. Okay, this capital F is defined in this in this manner. Capital F is equal to integral a to x f of t dt. Now this in fact this capital F is called the antiderivative of the small f. Okay, so a function f is said to be the antiderivative if f dash will be the same as small f. Okay, so this capital f dash equal to small f, then this capital F is called antiderivative, is an antiderivative of small f. Okay, in the next class we will prove the fundamental theorem of calculus. Thank you.